This is an example for area enclosed by the x-axis in a curve. So we want to find the area enclosed by the curve f of x and the x-axis when f of x is equal to x to the third minus 1. We're going to look at that area from -2 to +2. So when we're thinking about the area enclosed by a curve in the x-axis, this is different from just a regular integral. This is the gross area. And recall that what that means is that the area is always positive. So we're going to look at our graph of our function, and wherever the area is negative in terms of the regular integral, we want to be sure to make that integral positive so that we get the gross area. So let's draw this function. So here's a graph of that function, x to the third minus 1 from -2 to 2. And we're just going to look at the pieces of area that this has created. So this piece of area between x equals 1 and x equals 2 is positive. And in terms of a regular integral, this area from -2 to +1 is negative. So this area that I've drawn in green is okay to integrate normally. Since we're thinking about area enclosed, we want to take this negative area and we want to do the absolute value of the integral just for this negative portion in order to make the area positive. So instead of just doing a normal integral area, which would be integral from -2 to 2, x third minus 1 dx, that's not what we want to do, because that would count this red area as negative. So our enclosed area we're going to split our integral into two pieces, into the green and into the red piece. So the green piece would be the integral from x equals 1 to x equals 2. The reason we're using 1 is that's the x value when we cross the x-axis of our function x to the third minus 1 dx plus the integral from -2 to 1 of x to the third minus 1 dx. But since this piece is going to end up as a negative area and we're thinking about gross area, we want to take the absolute value of only this piece in order to make it positive. This first area from 1 to 2, that's already going to be positive. Okay, I'm going to evaluate these two separately, although we keep adding our areas together. But I'll just continue with one problem at a time. So integral of x to the third minus 1 from 1 to 2, that would be x to the fourth over 4 minus x evaluated from 2 to 1, which is going to be x to the fourth is 16 when we plug in 2. 16 over 4 is 4 minus 2 minus 1 to the fourth is 1 over 4 is 1/4 minus 1. So this first integral is going to be 2 minus -3/4, so 2 plus 3/4, or 2.75 for that first area that's drawn in green. And now the second piece of area, we're going to remember to keep our absolute value because we're going to want to make it positive at the end. Okay, integral here is x to the 4th over 4 minus x, evaluated from x equals -2 to 1. Keep our absolute value and first plug in 1. That would be 1/4 minus 1 minus, plug in -2. That would be 16 over 4, so 4 minus -2, so 4 plus 2. And that's going to give us absolute value of, this first piece is -0.75 minus +6 is -6.75, still within absolute value. So see, we got a negative in here because considering it as a regular integral, this area was negative. But now since we're doing gross area, we're taking that negative area and we're making it positive. So we get 6.75 when we take the absolute value. And we're going to add that to our area part 1 of 2.75, which was already positive, so we didn't need to do anything to it. Add these two chunks together, and we get that our area is 9.5. So really the only difference here is that, well, we need to split up our areas. So in this case, we had to split our area wherever we crossed the x-axis. So we had to split our area at x equals 1. So that's one of the main differences. Instead of just evaluating integral from 2 to -2 like we would have normally, we needed to split our graph into pieces. And then the pieces that were negative, we needed to make them positive. So make the negative pieces positive with absolute value. So those are the two differences really when we're finding the area enclosed by the graph and the x-axis versus just finding the area under the curve or the integral.